So it's great to be here in such a stimulating environment and also have the occasion to appreciate Jarkko and his many contributions to the field. So what I'm going to talk about is something that we did together with Nazim Fates, who's here, and Irene Marcovici a few years ago. And at least my side of the work was inspired by some discussions that we had with Jarkko some, I think, 9 years ago, or 9 or 10 years ago. Okay, so I start with an inspirational slide. So we have a wound that is healing. So you can think of this as a system that has some healthy or legal states, and then if you perturb it, you have to learn to use this. If you perturb it a little bit, then after a while it comes back to the legal state. Now, we have this cellular automaton, which has a very primitive but still non-trivial version of the same property. So this is Thom's northeast center majority rule, which I guess many of you are familiar with. So it's a binary two-dimensional cellular automaton, and the rule is just that we took, The rule is that we take the majority within this neighborhood. And this has this, for example, here the majority is black, and here is the majority is white. And this has this remarkable property that, this part is not remarkable, but that if you start with a configuration which is everywhere white except for finite region, then after finite number of steps, we fall back to the all white configuration. But the rule has symmetry with respect to black-white flip. And so the same is true for the black configuration, finite perturbations of the black configuration. And so you can think of it as, we call this property self-stabilization. So we have two types of legal configurations. These are like healthy configurations. And the healthy configurations are stable, so they are not changed by the cellular automaton. And if you make a finite perturbation of a healthy configuration, then it's rapidly healed. So the cellular automaton fixes or recovers from that perturbation. And now the question is, can we design cellular automata that have the same property but with a more complex set of legal configurations? And in particular, if the set of configurations is a subshift of finite type. And so this, you can think of it as a weak form of fault tolerance or tolerance against tampering by some adversary. And I will argue, since many of you are symbolic dynamicists, I will argue that it can also be interesting from the point of view of symbolic dynamics. Okay, so this is what I'm going to talk about. So I will first give a more precise formulation of the problem, and then I give you a bunch of examples, both examples that are simple and examples that are difficult. And then I will talk about time complexity of this kind of self-stabilization. And at the end, if I have time, which I'm not sure if I will have, I will talk about stabilization against not finite perturbations, but against random perturbations of a legal configuration. Okay, so the formulation is quite simple, as you can guess. So I have a subshift of finite type, which I call X, which plays the role of the legal configurations. And then I say that a cellular automaton F stabilizes this set of legal configuration, this subshift of finite type, if first of all the points in X are fixed points, they are not changed by the cellular automaton. And second, if I start with a finite perturbation of an element of this subshift, then in finitely many steps, the cellular automaton erases that perturbation and goes back to perhaps a different point in the same subshift of finite time. Okay? And the time that it takes this, to go back to this subshift of finite time, we call it a recovery time. Okay. So for example, Thom's cellular automaton that we just discussed a minute ago stabilizes this subshift, the subshift that has 2 points, the all white and the all black. So let me just point out that in this setting, I don't require the alpha beta of the cellular automaton to be the same as the alpha beta of the subshift of finite type. But on the other hand, so it can be potentially can be larger alphabet. But on the other hand, I don't want to cheat. So if the alphabet of the cellular automaton is larger, then the perturbations can come from these larger alphabets. Okay, so the cellular automaton has to fix perturbation, recover from perturbations that are from this larger alphabet. Okay, so now the question is, which subshift of finite type can be stabilized by cellular automata, and which of them can be stabilized efficiently? That means the recovery time is fast. Yeah. So okay, I said efficiently, but there are different ways that you can think about efficiency. So one, I think the most natural that I will talk about is the speed of stabilization, the recovery time. But you can think of also you can think of the number of extra symbols that the cellular automata requires as a measure of efficiency, or the radius of the neighborhood. And so this Thom's cellular automaton stabilizes that particular subshift very efficiently. So the recovery time is linear, there is no extra symbol, and the neighborhood is very simple. So it is as simple as it can be. So there are 3 elements in the neighborhood. Okay, so let me just quickly go through the way that Thom's cellular automaton stabilizes this subshift of all white, all black. And again, some people are familiar with. So just imagine a finite perturbation of the all white configuration. And so everywhere is white, and there are some finite number of black positions. And if I consider a right rectangle of this form that surrounds all the black sites, then you can verify very easily that after each step, this triangle just shrinks. So if you look at all the points, all the sites that are outside this blue triangle, they're not going to change, because the majority of the colors in their neighborhood is white. So here, here, and here, and here. But on the other hand, if you look at, for example, this one, so that those that are along this edge, that are inside the blue triangle, those also have majority white. So that means that in one step, the hypotenuse of this triangle just moves by one step. And then after a linear number of steps, the triangle disappears, and a legal configuration is reached. So that is the property of this cellular automaton: linear recovery, so stabilization in linear time. And of course, by symmetry, the same argument holds for all perturbations of all black configuration.
So if you have any deterministic direction, it can be fixed, right?
Sorry, say again?
If your subshift has any deterministic direction, it can be...
Deterministic? Yeah, I will talk about it, yes. So the question was whether the same kind of thing can be done when the subshift has a deterministic direction. Okay, so now I want to consider simple examples. In a nice class of simple examples are K colorings. By the way, for the most part, I will focus on two-dimensional subshifts. So K coloring of the K coloring subshift consists of configurations that are configurations of colors with K colors, and the neighboring sites. So the neighboring sites must have different colors. And this class of subshifts is studied a lot in symbolic dynamics, as you have seen from the other talks. So let's start with K equal to 2. This is two coloring, the subshift of two colorings. It consists of only two checkerboard configurations, and the even one and the odd one. And so if I have a finite perturbation of, let's say, the even checkerboard configuration, we want to know whether we can fix it with the cellular automata. And the answer is yes, and there are different solutions. So one simple way to do it is just based on Thom's cellular automaton, and you just essentially do the same thing, except that instead of majority among A, B, C, you flip B and C and take the majority among A and the flipped versions of A, B, and C. And this will work exactly like in Thom's cellular automaton. A different solution is to, in the checkerboard, in the even checkerboard, there are 4 sublattices that are constant, that are uniform configurations. So you can, instead of Thom's neighborhood, you can look at this neighborhood, which is just from the same. So for each side looks at only the neighbors within the same sublattice, and then you apply the Thom's rule over this neighborhood, and it works as expected. Okay, and you can extend this last argument, last example, to say that every finite subshift of finite type can be stabilized by cellular automaton in linear time, and without any additional symbol. Okay, so the next simplest family is when K is larger than a subshift of finite. For example, there are only finitely many elements, so it's very simple. Okay, so now when K is larger than or equal to 5, let's focus just on 5 colorings because the others are even simpler. We have this key property that I don't know who came up with the name for it. It's a single site fillability, and we have this property that whenever we have 4 colors A, B, C, D around a square, around a site, no matter what are those colors, there's always a 5th color that we can put here in a legal way. So it's very easy to fill in gaps. And based on that, we can design a cellular automaton which works very similarly to Thom's cellular automaton, and except that I guess we can do it in different ways, but the one that we have is that we look at only the positions that have a fault either on the upper edge or on the right edge, and then and we notice that if we apply that rule, that filling rule, into such a position that has a north or east fault, then no new fault is generated. So now if I take this kind of blue triangle that covers all the points that have north or east faults, then we can apply the same argument to show that in linear time, the 5 coloring subshift is stabilized. And in fact, the same argument works for any subshift of finite type which is single site fillable. Okay. Now the case of 4 colorings is a little bit more difficult because the four colorings are a bit more rigid. But still, so these 4 colorings have kind of similar property. Now if they are what we call strongly two-fillable. So if you look at a 2 by 2 square, and if you choose any colors for the neighbors of this 2 by 2 square, let me just emphasize that I don't require these colors to be consistent with each other. So it can be that A1 and A2 are the same. Yes. No matter how I choose these colors, there's a way to fill in this in a legal way. So there's a way that I can, which is consistent with itself and with these colors around. Yes, so this 4 colorings have this property. And again, we can construct a cellular automaton that stabilizes the 4 colorings, or more generally, any subshift of finite type which is not just 2 by 2, but or L-fillable, strongly L-fillable. And now here, the idea is that there's a way that came up, Irene and Nazim came up with, that there's a way that the cellular automaton can locally identify a family of 2 by 2 faulty or L by L faulty squares that do not overlap and are not adjacent to each other. And then it's a non-empty family. So as long as there is a fault on the configuration, the cellular automaton can recognize such a family, and then it can fix them. It can correct them, and so that at every step, at least one 2 by 2 family of faults is corrected. And so after a number of steps, it will be correct.
To make sure that whatever you're doing, another adjacent site is not undoing it, right?
Yes, that's why I said that the cellular automaton can recognize a family of 2 L by L squares that are not overlapping and not adjacent. Okay, so that we are not going to do anything to the others that are not overlapping. This. Yes, so now in this case, at least this argument, the argument that we have is that the stabilization, well, at every step, at least one 2 by 2 faulty block is corrected. So the stabilization is not linear anymore, but it's quadratic in the diameter of the region of perturbation. Okay. Now the next case is, well, the only case which is remained is k equal to 3, the 3 coloring subshift, and we are stuck here. And if you're familiar with 3 colorings, you know that it's much more rigid than 4 colorings or 5 colorings. And we don't know. We don't know if there is a cellular automaton that stabilizes 3 colorings. And there's a good reason for it, because, let me show it here, because for 3 colorings, it is possible to perturb a valid coloring in such a way that, well, in a very large or arbitrarily large region, in such a way that only one fault is introduced. So here I have, this hatchet region is the original configuration, and this large square is the perturbation. And I have done this perturbation in such a way that everywhere the coloring rule is satisfied except in this position. And you can,
This is around this single perturbation, and they sort of propagate all the way to the boundary.
right. I mean, the way that we understand this is using connection between 3 colorings and the 6 vertex model from statistical mechanics. And so so if you put arrows on the edge between the sites, and the arrow is always like this, that the site which is to the left of the arrow is 1 less than the site which is to the right of the arrow, modulo 3. And
Clear about the definition.
Yeah.
You always start with an element which is homoclinic to an actual element in the shift space, and that's what you want to correct?
no, even more. So oh yes, that's correct. That's correct. That's good. That's correct. Yes. Yes, I always have this. I come from a correct asymptotic family. Yes. So now if you draw these arrows, then it turns out that this every vertex here, it has exactly, in a correct coloring, every vertex has exactly 2 incoming arrows and 2 outgoing arrows. And in this particular figure, you see that these arrows do not match. And if I want to correct it, I really have to correct the whole region, or a region which is proportional to, its size is proportional to the size of this region. Okay, so this is an open question for us. If you have an idea, please let us know.
Correction, I might have to change an unbounded amount of.
Yes, exactly. Exactly. Okay. So let's go back to one-dimensional case. This is the case in which we have a solution, and this comes from, well, something similar to Thom's rule. Is a cellular automaton that was invented by Peter Gatch and Guillaume and Levin in 1977. And it has this property. Well, it's more complicated than Thom's rule because it's one-dimensional. And for instance, it is not monotonic. But still, it has this property that it stabilizes the subshift all white, all black in linear time. And this is not the only example. So at some point, Yarko and Bastien Leclerc came up with another example which is as simple, but perhaps the analysis of this one is a little bit easier. It's a bit easier to understand how it does the correction. It has the same property that it stabilizes this subshift all white, all black in linear time. Now we can extend this to essentially all subshift of finite type. We can come up with some cellular automaton, the one-dimensional cellular automaton, and well, the one that we came up with has extra symbols, but nevertheless it satisfies the definition. And so the only thing that we require is that the subshift of finite type is non-wandering. So, for example, this is an example of a non-wandering cellular subshift of finite type. So that means that there is no transient element in this subshift. So you cannot, anyways, it's there, I guess. There is, maybe about the same time or even earlier, Ilkka Turma came up with another solution for in one dimension which doesn't require extra symbols, and it doesn't, it's not restricted to the non-wandering cellular subshift of finite type, but it's more complicated nevertheless. So here, the idea that we use is that if you know which region is perturbed, then there is this very simple sequential procedure to fix this perturbation from left to right. But on the other hand, implementing that in a cellular automaton is not as obvious because there can be regions of errors that are far from each other. But nevertheless, you can do some sort of signaling we do some signaling and at the same time implement this sequential procedure in every island of errors. And we can show that eventually in linear time, everything is stabilized. Okay, back to the two-dimensional case. Natural questions: can we have a subshift of finite type which is aperiodic and can be stabilized by a cellular automaton? And the answer is yes. And this has to do with what Nishan suggested. So if I have a subshift of finite type which is deterministic in one direction, for example, northeast deterministic, then we have a stabilizing cellular automaton for it. Yeah, for example, so to clarify this notion, so this subshift of finite type which has two symbols 0 and 1, and the constraint is that the sum of the elements in this kind of neighborhood has to be 1, sum modulo 2 has to be 1. This is northeast deterministic. But on the other hand, there are aperiodic, there are many examples of aperiodic tile sets that are deterministic, even in more than one dimension. There was discussion of that before. And yeah, so we have this theorem that we can, if you have a northeast deterministic subshift of finite type, there is a cellular automaton which uses some extra symbols and stabilizes the subshift in finite, in linear time. Let me just emphasize that we cannot just naively apply the deterministic rule, because if we do that, then there's a possibility that the faults will propagate and become larger and larger. But nevertheless, we can apply the idea of the one-dimensional construction, and we can essentially apply, implement that in this 2 dimension, and it will work. Okay, now let me talk a little bit about the complexity, the time complexity. I'm changing the point of view to the problem of the complexity. The first thing that I wanted to mention is that, which makes it perhaps interesting from the point of view of symbolic dynamics, is that the recovery time is essentially invariant under conjugacy. Well, in particular, if you have 2 subshifts of finite type which are conjugate, and one of them has a cellular automaton that stabilizes it in time t, in time, let's say, tau n, then there is another cellular automaton that kind of stabilizes the other one in essentially the same amount of time tau n plus some constant. And this is, I mean, it's not difficult to show that, but at the same time, it's not that obvious, because I remember that, well, I mean, the alphabet of these subshifts are different. So perturbations in, the finite perturbations in X do not necessarily correspond to finite perturbations in Y. But nevertheless, we can essentially trace or emulate. If you have a cellular automaton that stabilizes X, then we can just emulate the performance of that to have a cellular automaton that stabilizes Y. Now, having this in mind, then you can think of the best recovery time that we can have. So if you consider all cellular automata that stabilize subshift of finite type, there's one or a family of those that have the smallest recovery time, then that's best recovery time can be thought of as a sort of, so you can think of it as a measure of complexity of that subshift of finite type. So this is a measure of complexity. So how much time do I need to spend using a local and decentralized procedure to correct perturbations and that subshift of finite type? It's a little bit reminiscent of this notion of logical depth. I guess I don't know anything about it. Maybe the experts would. Here, let me emphasize that again. So we don't know if every subshift of finite type has a stabilizing cellular automaton, right? In 3 colorings is an example, but nevertheless, so this theorem says that if one of them can be stabilized, the other one can also be stabilized, and with the same recovery, with the same best recovery time.
Do you know any example which can be you don't know?
3 colorings is an example that I don't know. We don't know whether it can be stabilized.
Example where you cannot stabilize?
Cannot stabilize?
Yes.
No, but okay. In a moment, I will show you an example in which cannot be stabilized efficiently. Okay, so let me just going back to just summarizing what we have so far about the recovery time. So the best recovery time for some classes of subshifts of finite type. For one-dimensional subshift of finite type, the recovery time is at most linear. For two-dimensional K colorings where K is either 2 or larger than or equal to 5, again the stabilization time is linear. For 4 coloring, it is at most quadratic. For 3 colorings, we don't know if it is finite or even it can be infinite. That means that there is none. Yes?
Can I just clarify? In the deterministic SFT case, when you say that you need more letters, you don't need them in the cheating sense. You need them in the nice sense that you are going to be more correct.
Yes. So the new symbols can appear in the perturbations. Yeah. Yes. And then we have also this that every deterministic SFT can be also stabilized in linear time. So any negative result, and here comes the result that unless P is equal to NP, you can there's a two-dimensional subshift of finite type which cannot be stabilized by any cellular automaton in polynomial time. That subshift of finite type that we have here, we don't know if there is any cellular automaton that can stabilize it, but at least we know that there is no cellular automaton that can stabilize it in polynomial time, unless P equal to NP. And this is the idea is based on this problem, square tiling problem. So if you have a fixed set of Wang tiles, and then you are given a square along with colors of its boundary, and the question is, can this coloring of the boundary be extended to the square? And this is, I didn't find it written anywhere, but it's a folklore result that you can find. You can construct a finite set of Wang tiles for which this problem is NP complete. Okay. Now, you just think about it. If you have a cellular automaton that stabilizes that particular subshift of finite type, or some subshift of finite type, then perhaps not exactly this problem, but a variant of this problem can be solved by just simulating that subshift, that cellular automaton. In particular, if I have a square here, a square that contains faults, and then if I apply the cellular automaton, okay, so I have to say that I'm assuming that the cellular automaton stabilizes in polynomial times. Okay, so if I have a cellular automaton that stabilizes in polynomial time, then this square of faults will be corrected in polynomial time. And if I look at a margin here of length, of width, 2 times the stabilization time plus 1, then at the end, the only part which is changed is this inner square, which has which is this inner. So the original square plus a margin of length with the stabilization time, which is changed. So there's a different version of the tiling problem, the square tiling problem, which is solved by this. And this is what I call the global tiling patching problem. So we are given a tiling. So we are given a square of size n, and we have a margin of size, I don't know, so some length, some width, which is polynomial, and we have a globally admissible pattern here. And the question is, can we patch this? Can we perhaps modify this inner square and make a valid tiling? Again, using the other example, the original version of the problem, we can modify that use that subshift of finite type to construct a subshift of finite type for which for any polynomial margin the problem remains. This problem is NP complete. Okay, so I guess I have maybe a few minutes. Yes. So let me talk a little bit about stabilization if we start not from a finite perturbation but a random perturbation. I spare you the formulation because it's not exactly clear what you want to have. Essentially what you want to have is that if you start with a random perturbation where the density of faults is, well, let's say we start with a Bernoulli random perturbation. That means that the perturbations at different positions are independent of each other, and the density of modified positions is sufficiently low. We want the cellular automaton to eventually converge in product topology to some element in the subshift, and perhaps we want some additional condition that we don't want to converge to something which is completely different. We want to have this property that, let's say, the density of positions that are different from the original unperturbed configurations is small. And so here is a theorem. The theorem says that if you have a cellular automaton, the nice thing is that we can connect it using ideas from Peter and Duran-Robertson, the famous paper. We can use a cellular automaton that stabilizes against finite perturbation, and that cellular automaton, as long as the stabilization, so the recovery time is subquadratic, then the same cellular automaton stabilizes against finite against Bernoulli perturbation. This is in any dimension. This is in any dimension.
But you allow perturbations only in the initial moment?
Yes.
During the recovery
yes.
also?
Only in the initial moment. At the beginning, we have a Bernoulli perturbation, and then afterwards, everything is deterministic. There is no fault afterwards. Okay, so let me just quickly go through why this is true. So just imagine the one-dimensional case, but in a higher dimension it will be similar. So just imagine a configuration that has only finite region of perturbed region, and this is where this black region. Now, and suppose that the cellular automaton stabilizes this subshift of finite type in time rho. The recovery time is given by rho. So if the length of this region is L, the time it takes to recover is rho of L. Now, notice that in this recovery, only this margin of, first of all, the only things that are changed are this, the gray trapezoid, darker gray trapezoid. So that means that only a region of size L plus 2 times rho of L times the radius of the cellular automaton that are changed during this process. And furthermore, this process depends only on this margin of width 2r times the stabilization time. So that means that if I have any configuration, if I have an island of perturbation, which has correct unperturbed region of sufficiently wide, so we have a sufficiently wide margin of unperturbed region around this island, then this correction will happen independently of what is elsewhere, and it will not. So this correction will not sense what is outside, and also outside doesn't sense that there was a perturbation inside. And so So now if I have a configuration in which the islands of perturbation are sparse, that means that we can decompose it into non-interacting islands in the sense that I just mentioned, then that configuration is also going to be, the cellular automaton is going to recover from those kind of perturbations. And this is the idea that was developed by Peter in the context of reliable computing and then used, and we got the idea from the paper by Sasha and Andre and Dur.
Advertisement for Peter.
Yeah, but still, it was maybe easier for us to understand it. Yeah, so this is the idea that came up when I was visiting Jarkko at some point, and we were talking about the problem of density classification, and then we came up with this idea that you to use this sparseness idea. Yes, so now there is this notion of sparseness that I'm not going to formulate it more precisely, but you understand what it means. So here, I'm assuming again the time of the recovery is rho of L, rho, a function of the length of the island. And so in the paper of Sasha and Andre and Bruno Duran, there's a theorem. So they prove that if this rho is linear, again, so this is implicit in the work of Peter, but anyway. So if rho is linear, then there's always, then for sufficiently small Bernoulli parameter, you can always decompose the perturbation into islands, into sparse islands. And but then there's a much later work of Peter that shows that this is true even if rho is subquadratic. Yes.
So stupid question, but so you really mean that you have dimension d, but it's still about subquadratic?
Yes, that's true. Yes. Okay. Yes, that's the idea. So if I have a cellular automaton that stabilizes in subquadratic time, then it's also against finite perturbations. It also stabilizes against sufficiently weak Bernoulli perturbations. Okay, so here are some open questions. First of all, we don't know if every subshift of finite type can be stabilized by a cellular automaton, and in particular, the three colorings. Well, for three colorings, perhaps there were some ideas that it can be done, but with a very complex construction. But then the stabilization, even if it works, it will be exponentially, it would take exponentially long. So perhaps you would want to have a polynomial time stabilization. Now, in the case of four colorings, we had a solution which was in which the recovery time was quadratic, but so that means that it doesn't work if the perturbations are random. So can we have a cellular automaton that stabilizes four colorings in subquadratic time? Now, I didn't mention about the same problem if we allow the cellular automaton to be probabilistic, and that's something that is very interesting that we want to explore further. There are some surprising things. For example, the five colorings, the solution that we had was linear. If we allow randomness, then we can do it in logarithmic time. I guess not, I don't know. Well, at least logarithmic time. And for four colorings, again, we have some examples that, well, Nazim came up with that potentially it could be that the probabilistic solution works in logarithmic time, which is, yeah, so that would make it more interesting. And of course, there is a problem of stabilization if we allow random perturbations even during the evolution of the cellular automaton. That's a more interesting problem. Okay. So thank you, and happy birthday.
Are there any questions? I knew I should have gone here first.
Oh, thank you. I want to recommend a slight weakening of the stabilization property. So instead of just adding an alphabet, having making a factor of a cellular automaton. So it's just a cell by cell function, right? So a factor of a bigger cellular automaton, and
So do you mean that you start with this? You have a subset of finite type, and then you want to have an
alphabet
extension of
on
it.
which, like you can say that you can have several symbols, only one symbol consists of several ones, and only one of them is what you are really interested in, right? But the point is that then I want to weaken the condition. I don't want the result to be a fixed point of the cellular automaton. Only the factor should be the fixed point. Okay. In other words, that the rest could still be. Because if you allow this, then suddenly things become much easier, because you can run kind of an error correction thing forever. And
Okay.
So my question, you spoke about the letter P example, yes?
Sorry?
The letter P example, so I was thinking, what is the nature of the stabilization? Is because it's a space-time of a possible expansive cellular automata? Is because a polygonal subchief of finite type? I don't know. In which class?
So this
It could
letter
work.
Pierre was
No, I know, but I think
was deterministic.
It has a lot of properties. It's algebraic. It's a polygonal subchief of finite type. So why it works? In fact, it works because of which of these properties? Because maybe it's a much general.
So the property that we use in our construction is just determinism.
Okay.
But
so a space-time could work for any SFT that you produce in this way. Do you have a question?
Just a short one. So, what happens if you consider just the island structure, but not in the original, not in one plane, but in space-time? It also has some islands. Doesn't it give some kind of self-stabilization in the presence of temporal noise?
well, the problem is that these cellular automata that we have, if you perturb them, then they don't work proper anymore. Yeah, but you can imagine that if the solution works in the presence of sparse noise, then it could also work if you look at the sparse islands in the space-time. So you just imagine that in the space-time you only have sparse noise, very sparse noise, like we have just noise that occurs.
Just Bernoulli with small.
No, not Bernoulli, but I mean that there's a minimum distance between. If that could work, perhaps the same kind of argument that is used for reliable computing can be.
Suppose you're on the even shift. Now, of course, on the even shift, you cannot do this. But now it's conceivable that maybe you can use finitary windows instead of finite block windows.
Finitary windows.
And it's conceivable that you have some sort of machine that only has finite memory and can only see finite, but it is allowed to travel around finitary windows to decide what to do.
Wait, I didn't understand. You want to extend the cellular automaton that you don't require finite window, but potentially.
Right. But in that sense, will it? Finitary window, yes. So
You mean it can potentially be arbitrarily large
yes,
and infinite?
not infinite.
Because there's
I
no
guess.
measure here, so that
Yeah, so not infinite, but yeah, it could be arbitrarily large but finite. Do you think you could fix more things?
potentially. I didn't think about it. Yes.
Okay, this is the last question. Otherwise, we would get killed at the restaurant.
In the theorem about deterministic SFT, you say at the end that you used a similar argument as the one-dimensional case. Is it inspired by Hill-Quatorze construction, or is there a reason why the non-wandering assumption has disappeared?
Well, the non-wandering assumption makes sure that the left tail and the right tail are in the same asymptotic class. And they are, we don't have a problem with that. But in 2 dimension, if you have a finite perturbation, then the asymptotic class is known. Yes, so there's no problem to.
Let's thank Siamak again.